Hello world, it's me. This is the third video on the design of this AD85 base STD Bus single board computer. In this video we're going to finish up by looking at the signals required for the board to work in an STD system. So pretty much everything covered in the first video could be for any generic AD85 single board computer, but now we're going to talk about the signals that are required for the STD bus. I'm going to take a lot of shortcuts here and just look at how the STD signals need to be handled on this board. We're not going to get in very far into the STD bus signal requirements at all. If there's general interest in STD bus specifications, I can do that in a later video, but this will serve as a nice primer on the bus signals. As I mentioned in the first video on this board, the core components of this board, this processor board, are the memory decoder, the processor, the 8155, and that's all fairly generic, and it was from a project that I started. This is the SBC85 single board computer. So did this a few years ago, and basically the core of this board is the same as the core of this SBC85 board. So we've taken that core and kind of shrunk it down, and then on each side we have the specific additions to make this core design STD Bus compliant. The STD connector is shown in the top left. Below that we have control signal drivers, and then up here on the left hand side we have the pull-up resistors on each of the bus lines. So for TTL based interface, these are 4.7K. For CMOS, these would be 10K pull-up. So all of the lines that are coming out to the bus have this 4.7K pull-up. Now over on the right hand side we have the drivers for the data byte and the 16-bit address. In the bottom right, this is a address latch. It's not actually part of the STD bus. As we can see, that's required for the core design. This is simply latches the low address byte off of the data bus when the AALE is strobed. So I should have called that out as part of the core design. Now on this schematic, any net name that begins with a little lowercase b means that it's connected to the bus. So that's a bus signal. We can see that the bus signals all have this lowercase b. If you're interested in the STD bus, you may want to get a copy of this STD Bus Interfacing Bug Book. It's a classic, but the biggest downside is that it isn't all that useful for anything beyond the very basics. They spend a lot of time talking about the same boilerplate that's in some of the other bug books, but for STD, it's fairly limited. There is the nice appendix in this, which is the STD Bus Standard, but that's also printed pretty much verbatim in all of the manufacturers' data sheets. But the second most useful thing in this book is this professionally generated STD 8085 signal map bookmark. And that's what I'm using for the basis of this board. I don't know when I made this. I'm pretty sure it was just lifted from a Prolog STD catalog or a training document. I'm not sure if I was keeping this poorly typed signal. There was a false start on that side. Or if I was keeping the artwork that's on the other side that my daughter drew when she was little. If it was kept only for the artwork, I should probably go and find the original source of the data, but the information does seem to be pretty legit. So this is basically how the STD lines are derived off of the 8085, and this would be, of course, processor specific, but this would be how they were derived for the 8085, and so that's what I used when I was creating this schematic. But as I mentioned, these specifications in this STD interface book are printed pretty much verbatim in all of the catalogs. The version that I like the best is the Win Systems one. It's the most current. It's also available online as a PDF. So you can get this, I think I showed you last time. You can get the STD bus specifications, and you can get best practices and so forth. So you can find this online. That's probably the best version that you want to start with. So all of these have the pinout for the STD bus, and STD specifies that the 5 volts are on pin 1 and 2. Remember that the pin numbering, all of the odd numbers are on the component side, and even numbers are on the solder side. So this first pin is pin 1, and then pin 2 is the one on the back side. So for STD bus, pin 1 and pin 2 are 5 volts. The next finger is going to be pin 3 and pin 4, and that's the digital ground. So when you're looking at a card online, if you're not sure it's STD, one of the easy ways to tell is if these don't appear to be the main power traces for the 5 volts and the ground, then chances are it's not STD. Now over on the right hand side are the auxiliary power and ground. So there may be power traces coming off the right hand side also. We'll talk about those in a little bit. The next fingers after the 5 volts and ground are the bias voltage. So this would be minus 5 volts, but we don't need minus 5 volts on our board, so we're just leaving those disconnected. And as I mentioned, 55, 56 are for the auxiliary power. And now on STD, unlike the 5 volts, since these are presumed to be fairly low current, they're not duplicated on the front and the back. So the component side is the plus 12, the solder side is the minus 12. And then the next pin in is the auxiliary power ground, which is duplicated front and back. And the voltage for the auxiliary power, by the way, is not in the specifications, but usually it's 12 or 15 volts, depending on what was required for the system. Since we're making our own 12 volts on board with this Max 232, on this board, all of the auxiliary power and ground are just left disconnected. Now let's look at the signals, and as far as the signals go, let's first look at the input signals from the bus onto the processor card, because there aren't very many of them. There's only 9 that are marked as in, and that includes the 2 that are marked in or out, that are bidirectional. Of these 9 signals, we're really only concerned with 6. And we'll dispense first with the ones that we're not going to use. 2 of them are for system expansion beyond the 64K of memory and beyond the 256 I/O addresses. They're the I/O expansion on pin 35 and the memory expansion on pin 36. On this version of the card, we're not going to control or qualify these signals for any decoding. If somebody finds a use for them, they're both active low. They're on this card tied low using a cuttable trace to ground. So you can come back, you can cut the trace, you can use them for whatever application that you find. And if you find a good application, then maybe the next version of the card will include a use for them. You might want to patch this to an onboard signal, such as the not onboard read, and then use it on a memory expansion card as part of its address decoding. Or you could connect them to the outputs of the onboard output port, and that would allow you to use that output port to page an external card or something. So you can think of applications, but nonetheless, I just left them here as a user to tie to whatever they wanted. The next one we're going to ignore is the priority in, and to skip ahead a little bit to one of the output lines we're going to later ignore, we'll ignore its partner, the priority out line now, so we can get it over with. So we're going to ignore both the priority in and the priority out. These are used in a hardwired priority scheme where each card is a lower priority than those connected to its priority in, and that card is of a higher priority than those cards in the chain connected to its priority out. So basically, if the card sees its priority in go low, it means that somebody of a higher priority wants to use the bus. And if somebody else wants to use the bus, this processor should excuse itself. And then if this card wants to use the bus, it would use the priority out to signal any lower priority card that the bus is being used by this card. So the priority in, priority out on this card, we're just passing them through. They're just connected together. And we're ignoring that signal. We're not driving it and we're not reading it. We're just passing it through. The final signal that we choose to ignore is the auxiliary control. This is a loosely defined signal. It's basically up to the system designer. It's specified as active low, but other than that, it should be considered to be proprietary signal, maybe a system tick, a watchdog tick, some sort of a gating signal. User may want to connect the timer into this line or maybe bring it into an interrupt or the timer out. So it's brought out to a test point where the user can install a wire wrap pin and jumper it however they see fit to whatever on the board. The next 5 lines we are interested in, and they're implemented in this design, therefore bus or interrupt requests. These 5 are all active low. They're all open collector. They all have onboard pull-up resistors to keep them non-asserted if they're unused or if the card is just being used alone on the bench without a backplane. So these 5 signals are on pin 45. There's the wait request. And from our little chart here, pin 45, the wait request is just connected to the ready. So this wait request is an input. It directly drives the 8085 ready input. Pin 42, the bus request, it's inverted through a LS240 down here, and that drives the 8085 hold. Pin 44, the interrupt request is inverted, and it drives the 8085 interrupt input. Pin 46, the non-maskable interrupt request, inverted and drives the 8085 trap. Pin 48 is the push button reset, which goes to the reset in on the processor. It also is connected to the onboard pull down, the supervisory, and has this little RC that gradually pulls it up. So that's the push button reset. The last input is the system reset, and I'm going to talk about that a little bit more in a minute. Right now, let's go on to the output signals. The first thing to note, and this is a key to being STD bus compliant and allow DMA, is that the STD processor bus, or the master, must be able to relinquish the bus to other cards whenever they request it. So when this primary card relinquishes the bus is available for use by other cards, for example, to do direct memory access, or DMA, say from a floppy controller to a RAM card. Since DMA is quite literally hardwired to do memory transfers, DMA, of course, is faster than the processor could even consider running a block transfer program. So while it's not required to be compatible, DMA was a key aspect of any respectable STD processor card, and so I thought it was important to make sure that this card would be DMA compatible. That means that this card has two primary modes of operation. The first is where this processor card is driving all of the bus signals onto the backplane. And the second is where the processor is stopped and it's released all of the bus signals. And what that means is that most of the signals controlled by this card must be tri-stated onto the bus. That's to say, in addition to the card being able to drive the signal high or low, it can place the line into the third state, which essentially disconnects the line from the bus. And that, of course, is the tri-state. So when looking at these signals, most of them are tri-stated and put into a high impedance mode whenever the 8085 enables the hold acknowledge, or the HLDA signal. So somebody requests a hold, the processor finishes up what it's doing, it then asserts the hold acknowledge signal. And when that hold acknowledge signal is asserted, you can see a lot of these drivers go into their high impedance state and disconnect this board from the bus. So let's quickly go through and look at all of the lines that are buffered. And they're not just buffered for loading, a lot of them are buffered because they need to go into this high impedance state. The processor read and write lines are buffered, put onto the bus directly with the same names on pins 31 and 32. The 8085 uses its IOM signal to indicate if the current bus cycle is memory or I/O. If the IOM signal is high, it's I/O. If the IOM signal is low, it's memory. But the STD bus follows the Z80 scheme and splits the IOM into two independent active-low signals. I/O request, which is IOREQ, and the memory request. So IOM is directly buffered to become the memory request, and it's inverted to become the I/O request, because both of these are active-low. And since these four signals are needed by anybody that wants to control the bus, this board tri-states them when the HLDA, or the hold acknowledge, is asserted. I already mentioned that the two expansion pins, 35 and 36, are unused. Pin 37 is also unused on an 8085 system. Pin 37 is the refresh signal. It's used for a dynamic RAM refresh. It's generated by the Z80, and it's one of the four control lines that are defined in the STD specifications to be dependent on which processor is used. So we have the four lines, the refresh, the MC sync, status 1 and status 0. And depending on what processor you use, this tells you how it's derived. So while we're on this table, the M sync is on page 38. And that's just a signal that occurs at a known point in each machine instruction, and it's specified to be the inverted address latch enable, so the inverted ALE, and it needs to be tri-stated with an asserted HLDA. So the MC sync will vary on which processor is in the system when that occurs, but it should only occur once during each machine instruction. Then for the 8085, bus S1 on 39 and S0 on pin 40 are just inverted versions of the status 1 and status 0 respectively. And again, since these are required by anybody else that wanted to do DMA, these are tri-stated when HLDA is asserted. Okay, so that was pin 39 and 40. Pin 41 is the acknowledge for the bus request. And on the 8085, pin 41, that is just the inverted HLDA. Now on this board, the HLDA goes through the B half of this 74LS240, so it's always enabled. Since it's used in many places on this board, it's buffered again and then distributed. The fan-out loading was close, and I probably could have gotten away with using HLDA directly from the 8085, but I felt it was better giving it a good drive with this bus driver. It's not buffered quite as hard, but I did buffer the IOM over here towards the right. Pin 42 we already did. That was the input. It's the bus request, which is connected to the 885 hold. Pin 43 is the interrupt acknowledge. That's an output, and it's just an inverted buffered interrupt acknowledge from the 885. Passed through the part of a buffer that tri-states during the asserted HLDA. Pins 44 and 46 were the interrupt request and the non-maskable interrupt we already talked about. Pin 47 is system reset. Now for the system reset, that's a bit of a special case. On this board, the 885 reset output signal is first inverted by this 74LS240, and then it's buffered and tri-stated by the 244 to become the system reset on pin 47. In the original specifications, this system reset is just listed as being exclusively controlled by the bus master, but tri-stated by an asserted HLDA. But newer specifications call this out to be open collector, which, as I mentioned in my last video, is why I have diode coupled the reset line. But in the later specifications, it was not called out as being tri-stated with HLDA. And as I mentioned in the last video, none of the cards that I have actually had this as open collector. But they did have it tri-stated. So I raised the question on the Facebook STD group if anybody felt strongly either way about this, if it should be open collector or it should be tri-stated. And it prompted a discussion with Roger on the Facebook group, and Roger is also very active in our Intel MDS group. And after I mentioned that none of my cards operate the reset as open collector, Roger mentioned that maybe it would be worth double checking to make sure that they weren't pulling a fast one and creating an open collector by simply disabling the tri-state output. So I went back, I confirmed that they were not, but after thinking about what Roger said, I think that's a better solution than putting in that pull-down diode. So I took the diode back out and I made this a pseudo-open collector by eliminating the ability for this buffer to drive the reset line high. And the way that works is the 0B input is tied low, and the active low reset is connected to the output enable pin in pin 19. So when the reset goes low and enables the outputs, the output would follow the input and it will reset that line to low. So it'll actively drive that line low. But when the reset goes high, even though the input is still low because it's tied low, the output will be disabled and the reset line will float high by the pull-up resistor. For all practical purposes, this is open collector. We'll call it open collector a la Roger, but I've included cuttable traces if that technique offends you. But it is important to note that if anybody else pulls that system reset low, but it will not reset the 885 because that is the reset out of the 885. If you want to reset the 885, you need to pull the push button reset low, which is on pin 48. All right, so we were up to pin 49. The last two that we're going to talk about are both clocks. Pin 49 is the bus clock, which is just inverted and it's continuously driven onto the bus, meaning it's not tri-stated with the hold acknowledge signal. So pin 49, the clock, is always available. And pin 50, as I already mentioned, is the auxiliary clock, which is just brought out to a test point. So that's it for the control lines. The last two buffers are for the 16 address lines over on the right. They're U15 and U16. They're both 74LS541s, which for their placement was just a little more favorable pinout than the 244. Again, these are tri-stated when the HLDA is asserted. So like all the control lines, HLDA is asserted, all of the address is removed from the bus, and these lines are floated so somebody else can control them. The final connection is up here in the top right-hand corner. It's the 74245 bus transceiver. Now in this particular case, I decided to use a bus transceiver, and as you would expect, like all the others, the output is disabled when the HLDA is asserted. However, this one has a little bit more complexity. Now, under normal processor control, meaning when HLDA is not asserted, this card will drive the 8 bits of the address and data lines onto the STD bus. So normally with this transceiver, the direction is from the onboard address data bus from the 885 going out to the STD bus, and normally it's enabled. Unless, of course, the HLDA is asserted and then that's disabled, as I just mentioned. Putting that data onto the bus gives offboard cards insight to what's happening. It's useful, say, if you've got a bus monitor, but it's, of course, necessary for when the processor is writing to an offboard I/O or memory. But when the processor needs to read an offboard address for the memory or the I/O, the direction of this transceiver needs to change to allow data from the STD bus to be driven onto the onboard data bus and read by this processor card. So the direction pin is used to control which way this transceiver is driving. This receive or drive signal controls the direction. And the logic for that's created by this little bit of glue logic right in here. So if we look at that glue logic, these inputs are the onboard selects for the 4 memory blocks decoded as onboard memory. If any of these are asserted during the read strobe, the data bus contents are placed onto the STD bus. So that means it's an onboard read. In addition to that data going into the processor, that data is also put out onto the STD bus. But during the read of an offboard memory, the transceiver drives data from the STD bus onto the local processor AD bus, so that the 8085 can read whatever is out on the STD bus. Okay, so this flips back and forth with each read. If it's an onboard read, the bus transceiver drives data onto the bus. If it's an offboard read, the bus transceiver receives data from the STD bus. And that's why this line is called either receive or drive. So reading the STD bus during an offboard read, but otherwise drive the processor 80 lines onto the STD. There's one more exception, and that is that during the interrupt acknowledge, since the interrupt is another mechanism like the HLDA for an external device to place data onto lines normally controlled by the processor, if the interrupt acknowledge is asserted, this transceiver will again receive from the STD bus and drive the data onto the processor, because that now contains an instruction for the processor from the STD bus. So as a final override in this direction control logic, an asserted interrupt acknowledge allows the external device to jam an instruction from the STD bus onto the 8085 data lines during the instruction fetch. So that's what this last gate does, is it allows that interrupt to jam the instruction. All right, that finishes up this board. I'll put the fabrication files up on the STD85 project site. But remember, this is still a early version prototype. You can build the board if you want. I'll get this board submitted in my next board order, and I'll let you know when I get the board assembled and start to debug and test. As always, this channel is entirely fueled by likes, engaging comments and discussions, sharing, and subscribers. Thanks for watching. Talk to you later. Bye-bye.